Hi everyone, welcome back to C++ Real-Time Audio Programming with Bela. Over the course of these lectures, we've been using the C++ language to implement the building blocks of synths and audio effects. We're covering a number of different topics in these lectures, and today we're going to be looking at the analog inputs and outputs that Bela provides. We'll build some circuits and we'll look at the basics of control voltages as they're commonly used on analog synths. This will be the first lecture in which we work with electronic hardware, connecting some simple circuits to Bela. We'll focus mainly on the analog inputs, and briefly at the end on the analog outputs. In the next lecture, we'll look at the digital inputs and outputs. I'll introduce how to work with an electronic breadboard, and we'll discuss the basics of control voltages as they're used in synthesizers. By the end of this lecture, you will have made a voltage-controlled oscillator and a simple musical instrument. As always, you can find the companion materials on the GitHub link at the bottom of the screen. This will include both code examples and a parts list. Specifically, what you'll need for this lecture is either a Bela starter kit or a Bela mini starter kit. The Bela starter kit provides both analog inputs and analog outputs. The Bela mini only provides the analog inputs, but you'll be able to complete most of this lecture using the Bela mini. Beyond that, you'll need a few electronic components for this lecture, including a breadboard, 3 potentiometers, a force-sensing resistor, a couple extra resistors, an LED, and some jumper wires. I'll build these circuits as we go along. Here's a brief overview of the Bela hardware, which we first saw in Lecture 0. In addition to the audio output, which we've been using, we'll also be working with the analog inputs and analog outputs on the Bela board, so take a note of where those are located. On the Bela Mini, we have most of the same capabilities. We don't have the analog outputs, however we do have the inputs, which are located in a slightly different place. At any time, you can always find the pinout for the analog and digital pins by going to the interactive pin diagram in the Bela IDE. Just mouse over each of the pins and it'll tell you its function. In this class, we'll be building our circuits on breadboards. A breadboard is a convenient device for connecting together electronic circuits without needing a soldering iron. You put the components into the holes on the board, and metal strips that run inside the board connect different holes together. So the trick of working with the breadboard is understanding which holes are connected to which other holes and why. The first thing to know is that each column of 5 holes is connected together by a strip of metal inside the board. Therefore, any 2 wires that are connected into the same column will be connected together by the breadboard, and any 2 wires that are connected in adjacent or different columns will not be connected together. Simple enough. The same thing is true of the other side of the breadboard. However, the left and right halves of the board are not connected together. The reason for this is that the breadboard is also designed for you to put chips in it. The chips typically sit across the break in the middle with 1 row of leads on the right and 1 row of leads on the left. The breadboard also gives you long rows on each end of the board. These are connected together across their entire length, though note that the strips on the left and the strips on the right are not connected to one another even though they have the same color labels. Remember, the breadboard is just a piece of plastic with pieces of metal inside of it. Making it do the right thing is up to us. The typical use for these rows is to carry signals for power and ground, which are used over and over again throughout a circuit. What I mean by ground is the 0-volt reference point of our circuit. Typically speaking, whenever we talk about voltage levels in a circuit, we are usually talking about voltage levels with respect to ground. And nearly every circuit that we're going to build is going to require a ground connection as well as connections to the Bela digital or analog pins. Before we go any further, I'd like you to build up your first circuit on the breadboard. One important note is that Bela provides 2 different voltage sources on the board. There's a source of 3.3 volts and there is also a source of 5 volts. While either 3.3 or 5 volts is acceptable for the analog inputs and outputs on Bela, the digital pins on Bela are not 5 volt safe. These pins hook directly up to the processor on the BeagleBone, and if you put 5 volts into them, it will damage the CPU and you'll find that the board doesn't boot anymore. Therefore, in all of our circuits, we will always be working with 3.3 volts to make sure that we stay safe for both digital and analog circuits. Here you can see a diagram of the circuit to wire up. This is going to require 3 potentiometers, your breadboard, and a series of jumper wires. I recommend that you start by wiring up the power and ground connections. You can see here that these are connected to pins labeled P9-1 and P9-3 on the Bela board. P9 is the name of one of the big rectangular connectors that is on the edge of the Bela board. The upper left-hand corner is ground, and the row right below that is 3.3 volts. Wherever possible, I recommend that you follow the color code of using black wires to carry ground signals, red wires to carry power, and other colors to carry other kinds of signals. This makes it easy to look at your circuit and understand what it's doing. If you have a Bela Mini, you can use the same breadboard circuit, but the power, ground, and analog inputs are in slightly different places, as shown here. Once you've finished wiring this up, open the Bela IDE, go to the example projects, and open the project called Scope Analog in the Analog section. Run this, open the Bela oscilloscope, and you should see 3 waveforms which change as you adjust the pots. This example only works with the first 2 analog inputs. I'm having you use 3 potentiometers because we'll use the third one later, but you'll see 2 analog inputs plus a sine wave that is generated as a result of the sketch. Here again is the circuit that you need to build. Pause the video, build this up, and then run the example. Okay, I have here my circuit with 3 potentiometers. Notice that the top one goes to analog input 0, the middle to analog input 1, and the bottom one to analog input 2. I can then go to the Bela IDE, I can make sure that the Scope Analog project is open, and I can run this project. I'll then open the Bela oscilloscope here. When I adjust the potentiometers, we'll see the signals appear in the scope. And in addition to the 2 analog inputs shown in blue and green, we can see in red a sine wave which is being synthesized by the example project. So this shows that our analog inputs are working. Let's now talk about how analog I/O works on Bela. One of the things that makes Bela special is that it treats its analog inputs and outputs as sampled signals almost exactly like audio. What this means is that your analog inputs are always sampled for you automatically. Your Bela code never needs to ask the hardware to take a reading. It's already been done for you, stored in a buffer, and it's available for you just like the audio signals are. Effectively, the analog input buffers are signals representing voltage with respect to time. And let's talk about each of these in turn. Bela features 16-bit analog-to-digital converters with up to 8 separate inputs. Unlike the audio inputs, the analog inputs are DC coupled. What that means is that the analog inputs can measure constant voltages as well as changing signals like audio. The usable range for the analog input is between 0 and 4 volts, although unlike the digital pins, the analog inputs won't be damaged by a 5-volt input. The usable input range between 0 and 4 volts is converted in the Bela software into a value between 0 and 1, which is returned to your code as a float. This gives us the first things that we need to know to understand the correspondence between hardware and code. Specifically, if 0 volts corresponds to a reading of 0 and 4.096 volts corresponds to a reading of 1.0 in the Bela code, then what would a reading of 0.5 mean in voltage? Well, in this case, it would be half of 4.096 volts, or 2.048 volts. Turning it around, if we put 3.3 volts into an analog input, how would we find the expected value of the reading? Well, again, we know that 1.0 corresponds to 4.096 volts, therefore, our reading would be 3.3 divided by 4.096, which is a value of around 0.8. So already this tells us something important about what's going to happen when we build our circuits. Because we're using 3.3 volts as our power source for the analog inputs, that means that we're going to expect that our controls are going to return values no greater than around 0.8, and we might want to factor that into our code. So again, the analog inputs are signals representing voltage over time, and like any signal, they have a sample rate. Recall that the Bela audio input and output have a sample rate of 44,100 samples per second. For the analog inputs and outputs, the sample rate depends on how many analog inputs we use. If we use all 8 analog inputs, the sample rate for the analog will be half the audio sample rate, or 22.05 kHz. If we tell Bela to use only 4 channels, then the analog will have the same sample rate as audio, or 44.1 kHz. There's also an option to use only 2 analog channels, in which case you can sample them at double the audio rate, or 88.2 kHz. Notice that with 16 bits at a high sample rate, these analog inputs are actually themselves sufficient to capture audio signals. In fact, we have an accessory called the audio expander which makes it easy to convert these analog inputs into extra audio channels, though the analog inputs use a different type of converter than the audio inputs, so the quality will always be highest on the traditional audio inputs. Let's talk more about the analog sample rate. As you may recall, the sampling period of a signal is 1 divided by its sample rate. So if audio has a sample rate of 44.1 kHz, it has a period of 22.7 microseconds between each successive sample. Given that the default analog sample rate is 22.05 kHz, what would we expect the sampling period to be in this case? Well, it would be twice the audio sampling period, or 45.4 microseconds. Therefore, how many audio frames are going to elapse for each analog frame? The answer is 2. The reason that I bring this up is that it's a relatively subtle point in coding your C++ examples to use both audio and analog at the same time. And that is because we're doing our real-time processing in blocks, and each block covers a particular slice of time. So if that slice of time included 16 audio frames, how many analog frames would fit in the same space? Since it's 2 audio frames per analog frame, it will be only 8 analog frames in that block. And remember that there are 8 different analog input channels, each of which would have 8 frames within this block. In our previous Bela examples, we've written a for loop inside of render which stepped through each of the audio frames. This leads to an important question, which is, given a particular audio frame number, how are we going to find the right analog frame number that corresponds to it in time? Well, given that there are 2 audio frames for each analog frame, we can just divide the audio frame number by 2 to find the corresponding analog frame. But why doesn't that result in a fractional index? If, for example, I had audio frame number 3, I divide that by 2, I would get analog frame 1.5, and of course I can't read a fractional value out of an array. Why does this actually work? The reason that it works is that we typically use int for indexing arrays, so if our audio frame is an integer with a value of 3 and we divide it by 2, the result will also be an integer, the fractional part will drop, and we will just read analog frame number 1. Let's look at what we need to do to actually read the analog inputs on Bela. Remember, the analog data has already been sampled, just like the audio data has already been sampled, and it is available in an interleaved buffer for us to pull out and use in our code. Bela provides you this function called analog read, which is basically a convenience function for accessing particular elements within this interleaved buffer. So let's have a look at how this works. Here's the definition of analog read, and it takes 3 arguments. The first is this Bela context struct, which we've seen in previous lectures. This contains the analog data as well as information about the number of channels and the sample rates of the analog inputs and outputs. The second argument is which frame we want to read, and the third argument is which of the channels between 0 and 7. And you can see within the implementation here that all it's doing is looking into the interleaved buffer and finding the right element to return. That element will be returned as a float with a range between 0 and 1. Here's an example. We're calling analog read, we're passing it context, frame number 2, channel number 4. Here's a representation of our interleaved buffer where the numbers represent the different channels. Which of these samples would be returned into reading? Well, we have to look at frame number 2, which is actually the third of the frames, because remember our indexing starts from 0, and then we have to look at channel number 4, so it's going to be the third square with the number 4 associated with it, i.e. it is this one. Now the nice thing about the analog read function is that you don't have to remember anything about the interleaving of the buffer. I bring this up just so you understand how it works, and remember that the analog readings have always been captured for you before the render function even starts running. Let's have a look at what's going on in the scope analog code that we just ran. I've pulled out the critical bit here. Analog read is called twice, once for input 0 and once for input 1. Once we have that data, we rescale it using different functions. The first one is just multiplied by a value of 0.8, whereas the second one we pass into the map function that we saw a few lectures ago. This rescales the range from 0 to 1 to be between 100 and 1000 Hz. Now what on earth is going on here? This line of code is full of strange symbols. This line of code uses a variable called g audio frames per analog frame. The value of this is calculated inside the setup function as follows. The reason this exists is that we might run this example on a number of different Bela boards and potentially with different settings for the number of analog input channels, and we want to make sure that our code handles each of the cases correctly. Let's look at some simplified cases to see what's going on. Suppose that we knew that our analog sample rate was actually half of the audio sample rate, i.e. audio has a sample rate of 44 kHz, analog has a sample rate of 22 kHz. Then we could simplify our code like this. Our for loop is counting the number of audio frames in our block. There are half as many analog frames. So what we're going to do is we're going to use the modulo operator to look for the even-numbered audio frames. When we get an even-numbered audio frame, then we're going to read an analog frame at half of that particular audio frame index. It's really important to get this right, because if you pass n rather than n over 2 into analog read here, you may read off the end of the analog input buffer and your code could crash. Here's an even simpler case. Suppose that we knew that instead the analog sample rate was actually equal to the audio sample rate. In that case, we don't have to do anything special at all. We can just call analog read, pass it the frame number n, which is the same as the audio frame number because now they have the same sample rate. Very easy in this case. To summarize then, the reason that we're using the variable g audio frames per analog frame is because we don't necessarily know what the settings are when the program is being run, and I strongly encourage you in your code to be able to handle different sample rates and channel counts, or, at minimum, to check inside of setup whether you have the settings that you expect, and if you don't, to make the program quit. This is much better than having your program crash if it's put in an unfamiliar environment. Let's now apply this to a different example. In the previous lectures, we've been making a voltage-controlled oscillator, or VCO for short. This is one of the standard and fundamental components of analog synthesizers. A VCO takes as an input a control voltage, or CV. This is just an electrical signal which tells the VCO what frequency to oscillate at. Up until this point in the course, we've been doing this all virtually with sliders in the GUI, but from today we can actually do this as a literal electrical voltage at the analog input. A common standard that you'll encounter on analog synths is what's called 1 volt per octave. What this means is that every increment of 1 volt on the CV input produces a doubling of the frequency at the output. On Bela, we have an analog input that takes a range of 0 to 4.096 volts, and remember that this corresponds to a float between a value of 0 and 1 inside of our render function. Therefore, what would we read in render with 1 volt at the Bela analog input? Well, this would be 1 divided by 4.096, which is equal to about 0.2441. This brings us to the first coding task of this lecture. In the companion materials on GitHub, you'll find an example called VCO. This implements the two detuned oscillators we implemented a couple lectures ago, but it still relies on the GUI sliders and doesn't yet use the analog inputs. Therefore, that's your task. What you have to do is change this code from using the GUI to using the analog inputs to control the frequency, the amplitude, and the detuning ratio of the oscillators. When you first start, just use the analog read function to get these three values. You may need to use the map function to rescale the 0 to 1 range to the kind of range of parameters that the GUI provided for you. Once you have that working, then see if you can implement the 1 volt per octave CV standard. What you should do is have a minimum frequency of 55 Hz, so that if you read 0 on the analog input, you'll get 55 Hz out. Each additional 1 volt on the input should correspond to a doubling in that frequency. You'll find that when you make this change, you actually have a wider frequency range than you did when you started in the example. This example does have the Bela oscilloscope enabled, so you can check whether it's working correctly there, as well as listening to the output. Pause the video here, see if you can make it work. Initially, you can see the starting point in our render function. You can see that we're getting the frequency, the amplitude in dB, and the detuning ratio from the GUI sliders. We need to change this to use the analog inputs instead. And here's one possible solution, converting it to use the analog inputs. Notice first of all that we got rid of all the code at the top of render and everything has moved inside of the for loop. The reason that we've done that is that we have more than one frame of analog input available to us within the render function, so we actually have a much finer grained control than we did before, where we could only read the GUI once per block. So here's our code reading the three analog inputs. Notice that I'm converting audio frame number n into analog frame n over 2. This is making a big assumption, which is that I have 8 analog input channels and therefore half the sample rate. It would be a good idea to check whether that was actually true inside of setup, or to write the more elaborate version that we saw in the scope analog example earlier on. Once I have the 3 inputs, I'm going to use the map function to rescale them from their original range into the range that the sliders provided. Notice that this is my input range, which is going from 0 to 3.3 volts. Though if you just made this 0 to 1, that's basically fine, and you just won't reach quite the top of the range with the circuit that we have available. So here we're rescaling the frequency to be between 55 and 440 Hertz. We're rescaling the amplitude to be between -40 and -6 dB, and we are rescaling the detuning ratio to be between 0 and 0.05, and then all of this code remains the same as before. We can run this example then. And we can go over to the scope. And we should be able to see this change as we manipulate the potentiometers. So we'll turn the amplitude up, change the frequency, we can change the detuning ratio, Notice that the amplitude never goes quite silent because we specified a minimum of minus 40 dB. Now that example just remaps the sliders into potentiometers, but what if we wanted to implement this 1 volt per octave standard? We're going to need to change this line here, which calculates the frequency as a function of the analog input. And what we need to do instead is implement the formula we saw before, starting with our reference frequency, which was 55 Hz, and we're going to multiply it by 2 to the power of the input represented in volts. So the input range is 0 to 1, which corresponds to 0 to 4.096 volts. So what we can do is we can take input 0 times 4.096. That's the input range in volts. If we run it this way, we'll get a similar output, but we'll see that the frequency is controlled logarithmically, and that if we were to carefully measure the input voltage, we'd find each additional 1 volt produced a doubling of the frequency. Back over to the scope then. We'll increase the amplitude, and then gradually increase the frequency. You can see that we have a wider range of frequencies than before because we have nearly 4 octaves available to us. So we have successfully made a VCO. We could feed into Bela a control voltage from an analog synth and get out an oscillator waveform. In these circuits, we're using potentiometers, or POTs for short. Let's talk a little bit about how these work. They're sometimes described as a variable resistor, a resistor being something that resists the flow of electric current. The essential idea is that the potentiometer contains inside of it a ring of partly conductive material. When you turn the shaft, there is a metal wiper which moves back and forth along that conductive strip, and it effectively divides it into 2 pieces, one on each side of it. The way you typically wire up a potentiometer is that the outer terminals on the ends of that conductive strip go to your power supply and to ground, so 3.3 volts and ground in this case. And then you take the middle terminal, which connects to the wiper, and that becomes your analog input. What we're building is a circuit called a voltage divider. This is one of the most fundamental building blocks of analog circuits. It is essentially 2 resistors stacked on top of one another, and the voltage that is present at the middle point depends on the ratio of the 2 resistors. Again, the potentiometer is one big long strip of conductive material, but by placing the metal wiper in the middle, we effectively create a resistor on either side, and the ratio of those 2 determines our voltage, according to these formulas. We can calculate the output voltage as the power supply, 3.3 volts, times one of the resistors divided by the sum of the resistors. Every potentiometer will be specified with a total resistance from end to end. In this case, I'm using parts with a value of 10 kiloohms, so that means that R1A plus R1B always add up to 10K no matter where the knob is set to. There are lots of great tutorials online about electronic circuits, and I'll put some of those into the companion materials, but I bring up this voltage divider concept because it also helps us with another circuit that we can build. One really useful sensor is called a force sensing resistor, or FSR for short. An FSR is basically a pressure sensor. It has 2 terminals which form a resistor, and when you press on it, the resistance goes down. Now the first question in any situation like this is where could we find out more details about how this FSR works? Let's say that I have a very specific FSR and I want to know what its resistance is and how that responds to pressure. Well, the answer, as always, is look in the datasheet. Remember, manufacturers want you to buy their components. They will often provide really good documentation telling you everything you need to know about how a component operates and how you can use it. Interlink is one of the companies that makes force sensing resistors, and here's some examples from their datasheet. You can see that with no pressure, the resistance on the FSR is very high, but it rapidly drops with increasing force. Notice that the FSR only has 2 terminals rather than 3, like the potentiometer that we just wired up. How are we supposed to use this to convert a resistance into a voltage that we can actually read at our analog input? Well, the answer is the same circuit we saw before. We need to build a voltage divider. What we're going to do is we're going to use the FSR together with another resistor which has a fixed value, say 10 kiloohms, and we're going to use these as each side of the voltage divider. Here's the circuit that we need to build. The top side is the FSR. The little arrow through the resistor means that it has a variable resistance. And then the bottom half is the 10K resistor. And we can calculate the output voltage using exactly the same formula that we saw before. Leaving aside any mathematical formulas here, the intuition here with a voltage divider is like a game of tug of war. The midpoint is going to be pulled toward the side that has the lower resistance. So what we need to know in this case is which side will have the lower resistance. As we press harder and harder, is the resistance on the FSR going to go up or down? Well, we saw on the datasheet that the FSR resistance goes down as we press on it. Therefore, the top side has the lower resistance and the voltage is going to become higher. Your next task then is to build this particular circuit. You should remove the middle potentiometer from your board and replace it with an FSR and a 10 kilo ohm resistor. Resistors are readable by the colored bands that are on its package. In this case, 10 kilo ohms corresponds to brown, black, orange, and then probably a last band of gold most commonly. What we're doing here is we're using the amplitude control with the FSR rather than with the potentiometer. Without changing the code at all from before, see how the playing experience differs. If you're on the Bela Mini, the change is the same. Again, just switch out the potentiometer for the FSR. Once you've built this up and tried it the first time, play around with the input range for the FSR, for example, to see if you can make a wider dynamic range where when you don't press on the FSR, you don't hear anything. Pause the video here, give this a shot. And there we are. Same idea, but now with FSR instead of potentiometer. Let's run the code again. Here we are, we can go back to the oscilloscope, and now I can change the amplitude with the FSR, and I can change the frequency with the potentiometer, like so. And of course I can still change the detuning ratio. Now one thing that's kind of nice about using the force sensor is that it becomes possible to play the instrument percussively. Like so. Notice though that we still hear a tone even when there is no pressure on the FSR. That's kind of annoying. Let's change that. So what I'm going to do here is I'm going to stop the program and I'm going to change this decibel range so that instead of going down to -40, it goes down to -80. This ought to be quiet enough that we don't really hear it. We can also just have a check where if the input is close enough to 0, we just mute the output. But I'll run this code again with this new parameter range. And here we are. So what we can see here is that with the FSR held down here, this is a very simple musical instrument indeed, not the most convenient thing to play, but it's a starting point. The last thing we'll look at in this lecture is using the Bela analog output. As you might expect, the analog output works quite similarly to the analog input in that it uses sampled signals with a constant sample rate, the default value for which is 22 kHz for 8 channels. Like the analog input, the analog output is also DC coupled, which means that it can output constant voltages like control voltages. The analog output also takes a signal range between 0 and 1, which in this case corresponds to a range between 0 volts and 5 volts. Notice that's slightly different than the analog input. Here's the function we use. We call analog write. We pass it the Bela context. We pass it which frame within the block we want to write to. We pass it which channel we want to write to. And then finally, we pass it the value that we want to write. To see this in action, let's hook up an LED. Remember, this part is only available on the original Bela kit and not on the Bela Mini. We're going to hook up this LED and notice that you need a resistor in series with the LED. This is a different value of resistor than before. There's a range of values that can work reasonably, anywhere from about 220 to let's say 560 ohms should work about right. But you need the resistor to be in series with the LED. This limits the brightness of the LED and also protects both it and the board from damage. The final thing to know about the LED is that it is polarized. The long lead should go to your resistor and the short lead should go toward ground. If you put it in backwards, it won't damage it, it just won't light up. By the way, don't remove the potentiometers or FSR from your board because we're going to use them again in a moment. Just add the LED into an open space on the breadboard. Once you finish building the circuit, then open the example in the Bela IDE called Analog Output, and you can run this. What you should see in this example is an LED that is fading gradually on and off. And in fact, the example lets you hook up to 8 different LEDs, and they'll all fade on and off in a sort of chasing pattern. Here again is the circuit that you need to build. Pause here, build this up, and give it a shot. Let's talk more about the code behind this. We have a function called analog write, and its behavior is that it will write a value to an analog output at a particular frame, and then that value will persist for all subsequent frames in that call to render and in all future calls to render. In other words, we can call analog write just once, and the value will stay there until we tell it to do something differently. This is typically how an analog or digital write statement would work on other platforms. But here, the Bela core code has to do a bit of extra work to make sure it works with a sampled signal. If I call analog write and I write frame number 3 to a value of 0.5, what's going to happen is that that frame and each subsequent frame will all be set to a value of 0.5. Now this is fine, but it's not necessarily the most efficient if you knew that you were going to be calling analog write every single frame anyway. So we provide an alternative function called analog write once. The idea here is that it'll write a value to one frame and only one frame, which takes a little bit less computational power. So if I call analog write once with the same set of parameters, it'll store the value 0.5 into frame number 3, but leave the other frames unchanged. This brings us to our final task. We saw a couple lectures ago that detuned oscillators produce beat frequencies between them according to their sum and difference frequencies. These detuned oscillators are already implemented in the example, but what I'd like to do is have the LED fade on and off according to the beat frequency. So in this task, use the example called VCO analog out. This provides you some basic mechanics at the beginning inside of setup to prepare the analog output. In addition to the two wavetable oscillators, we have a third wavetable oscillator which functions as an LFO, or low frequency oscillator. What we're going to do is we're going to use this third oscillator and set it to essentially the difference between the two frequencies, and then we'll use the LFO to control the output value of the LED. So your job is to implement the code in render that sets the frequency of the LFO according to the center frequency of the oscillator and the detuning ratio. Then you need to call the process method of the LFO. For more details on working with this wavetable class, or C++ classes in general, see Lecture 5. When you're done, then call analog write once to write the output value to the LED, and you should see the LED fade on and off according to the beats of the oscillator. Try that now. Here's the completed example with the analog output. In addition to the two wavetable oscillators that we're using for audio, we have a third wavetable object which is representing the LFO. This is a great example of why implementing things in C++ classes is so helpful. We can easily create another oscillator just by making another object. Inside of setup, we're populating the wavetable with a band-limited sawtooth wave. You can see more about band limiting in the previous lecture. We're using that wavetable with both of the audio frequency oscillators, then we're recalculating a sine wavetable which we're using with the LFO. All of this was given to you initially. One thing to say about this is that the LFO output here for the LED has been scaled to be a different range than -1 to 1. Remember first of all that analog outputs have a range between 0 and 1 on Bela. But beyond that, the way that the LED works is that it takes a certain minimum voltage before the LED will start to light up at all. Therefore, what we're doing is we're rescaling the range of the table here so that the minimum output voltage that we'd expect to actually arrive on the analog output pin is around 1.5 volts, and that the maximum value gets up to around 5 volts. That'll make for a smoother fading on the LED. Down here in render is the code that you have to add yourself. In the previous example, we dealt with the rescaling of these ranges, and then we have to add a calculation for the frequency of the low frequency oscillator. Notice that it's just the difference of this frequency and that frequency. In other words, it's 2.0 times the frequency of the audio oscillator times the detuning ratio. This audio calculation is the same as it was before, likewise writing to the audio output and to the Bela oscilloscope. And then here we have the calculations for handling our low frequency oscillator with the LED. First of all, we call the set frequency method of GLFO to set the frequency of this oscillator to what we calculated up here. Then beyond that, we have to call glfo.process to get the next value of the low frequency oscillator. Finally, we're going to write that value using analog write. We're going to write it to frame n divided by 2. Again, we're making an assumption here, which is that we're using 8 analog channels, so it has half the sample rate of the audio. There are a couple things that we could do to make this code slightly more efficient. We could change from analog write to analog write once, as we discussed a minute ago, and we could also decide to write only every other frame. Notice that this loop is running once for each audio frame on Bela, but that there are only half as many analog output channels. Therefore, what's effectively happening is that we're overwriting each of these samples twice. It'll work absolutely fine, but if you're really concerned about maximizing the performance, you could work it out to only write half as often here. Let's run this code and see how it works. Okay, we see the LED light up a little bit. Now watch what happens here. I can turn the detuning ratio up, and the LED starts to fade on and off. I'll tilt this a little so it's a little easier to see. And the speed of pulsation will also reflect the frequency of the oscillator. So let's actually hear it by giving it some amplitude. And we can, of course, see this in the Bela oscilloscope at the same time. That's it for this time. Next time, we'll work with some more circuits using Bela's digital inputs and outputs. In the meantime, keep in touch with us on social media at Bela Platform, or if you have questions, you can always drop by our forum. You can see projects made with Bela featured on our blog, or go to the Bela knowledge base at learn.bela.io for tutorial and reference materials. Thanks for following along. Don't forget to click subscribe to be notified of new lectures as they become available. See you the next time.